Okay, so this is another video for Regents Review, Mrs. T's Chem Talk. We're going to do reference tables and we're going to do N to R. So looking at reference table N, it's the table for selected radioisotopes. And when we look at this reference table, we have things list for nuclide. We have a list for the half-life of each nuclide, their decay mode, and the names. So the first thing we're going to look at is the fact that the name dash a number, like gold dash 198, means gold with a mass number of 198. Remember that this atomic number comes from the periodic table or on table S, and when we find gold on the periodic table, its atomic number is 79, and that doesn't need to be given to us because of the fact that we can always find that number 79, the atomic number for an element, on the periodic table. So for each element, we're going to be able to look up the length of the half-life. For example, D is this many days, Y is years, MS is milliseconds, MIN is minutes, and you can see that they have varying times. The shorter the half-life is, the less time it takes for the substance to decay into more stable products. Remember that the half-life is defined as the time it takes for a radioactive substance to decay into, for half of the radioactive substance to decay into more stable products. Half of it remains after that time. The decay modes, remember B minus is beta, B positive is positron, and A stands for alpha. These symbols will be discussed on the next table in table O. And we can use these times for these half-lives to determine how much of a radioactive sample will remain after a certain amount of time. For example, if we start with 100 grams of cesium-137 and we allow 60.4 years to go by, before the decay starts, we have the 100 grams. After one half-life period, which is 30.2 years, that amount remaining divides in half to 50. After two half-life periods, which is another 30.2 years, we now have 25 grams remaining. So 30.2 years plus 30.2 years is the total 60.4 years. That means that after that time, we have 25 grams remaining as cesium-137. If we also wanted to look at cesium-137, put this over here a little bit further, cesium-137 will undergo natural transmutation and give off a beta particle. So any of the things that are found on table N will undergo natural transmutation, meaning that they will be the only reactant in the transmutation because it will decay spontaneously. One of the products will be the symbol for the decay mode, in this case beta, and the other product will complete the math problem. 137 plus 0 equals 137. Here the atomic number is 56, and a minus 1 gives us 55. And on the periodic table, element number 56 is Ba, so this would complete the decay equation for cesium-137. Moving on to table O. Again, table O has symbols for use in nuclear chemistry. Table O goes with table N. Remember that if we look at the symbols here, like for an alpha particle, the top number is called the mass number. The bottom number is called the atomic number. Mass number is protons plus neutrons. Atomic number is protons. And we can do mass number minus atomic number to get the number of neutrons in any species when we have the mass number and the atomic number. An alpha particle has a charge of +2. A beta particle has a charge of -1. Gamma has no charge. Neutron has no charge. Proton has a charge of +1. Positron has a charge of +1. If we want to talk about the penetrating power, alpha has the least. It has the most mass, so it can be stopped the easiest. And gamma radiation, which is just really pure energy, it has no mass and no charge. Gamma radiation has the most penetrating power. When we're talking about these as well, if we were to talk about a source of radiation from a lead block, if we had a negatively charged plate and a positively charged plate, a positively charged emission would go towards the negative plate, a negatively charged emission would go towards the positive plate. And that is just because of opposites attracting. If we go to table P, remember these are our organic prefixes. So if you see any name that starts with or has meth, eth, prop, bute, pent, hex, hept, oct, non, or dec in it, that is telling you about the number of carbon atoms. For example, methane has 1 carbon. Methanol has 1 carbon. And methanal all have 1 carbon. The endings tell us that they are different types of compounds, but the prefix meth means 1 carbon for all of them. If we move down to table Q, we use table P and table Q together a lot. Table Q gives us our homologous series of hydrocarbons, and each of these members of the alkanes or the alkenes or the alkynes will differ by the number of carbon atoms, and every extra carbon atom that's added will add an extra 2 hydrogens. So for the alkanes, the number of carbons gets doubled and then added to 2 to get the number of hydrogens. The alkanes will have all single bonds. The alkanes are saturated because single bonds are saturated, and the alkanes will undergo the reaction called substitution. Now, substitution, which we'll talk about in another video, always has 2 products. So that S actually goes with that's this S. So things that are alkanes have single bonds. Single bonds are saturated. Single bonds and saturated undergo substitution. Substitution always has more than 1 product, so we say that substitution has products. That would be methane, ethane, propane, butane, and so on. Alkenes and alkynes are both called unsaturated because alkenes each have 1 double bond and alkynes each have 1 triple bond. Our alkenes, I say double-double because when you have one double bond in the molecule, you double the number of carbons to get the number of hydrogens. So if you see, for alkenes, if you see C2H4, C3H6, C4H8, it doubles when you go from carbon to hydrogen. You know you have a double bond, and if it's less than double, it's most likely going to be an alkyne. Alkynes, remember, each have a triple bond, 1 triple bond. Moving on to table R. When we look at table R is our table of functional groups, and we're going to use table R in order to try to determine what kind of a compound we have when it's not just a hydrocarbon. So hydrocarbons, which were on the table before, have just hydrogens and carbons, as the name suggests, whereas these functional groups, these compounds with the organic functional groups, have other elements besides hydrogen and besides carbon. The first thing that we should look at is the name. The endings will tell us something about the type of a compound. Every time we have a chloro, a fluoro, a bromo, or an iodo, that's going to be not the ending, but that's going to tell us that we have a halide or a halocarbon. Anytime we end in ANOL, it's an alcohol. The word ether tells us it's an ether. ANAL means aldehyde. ONE means ketone. Anoic acid means organic acid. Anoate means ester. Amine tells us that it's an amine. Amide tells us that it's an amide. So these endings will follow the patterns for all of the others. We would just change the prefix. So if I hadn't had an acid, organic acid, with 6 carbons, it would be hexanoic acid instead of prop. The functional group is the piece that's different, that's not just C's and H's. The general formula tells us what is the group of atoms is bonded to the functional group. It shows us how it bonds to the functional group. For an alcohol, we should know by now to recognize an OH somewhere. An ether, chains of carbons are connected by an oxygen. For an aldehyde, there is a double bonded oxygen on an end carbon. For a ketone, there's a double bonded oxygen on a middle carbon. Organic acids have COOH. Esters are going to have a COO in the middle of the chain so that on the other side of the COO there's a C. Amines have an N somewhere. Amides have an N with a double bonded O. So if you look to see what's not just C's and H's, you can usually find what kind of a compound you have using table R. So this is the end of this video for Mrs. T's Chem Talk. This is Regents Review's reference table. There will be at least one more video for the periodic table and another video for table S and table T. So come back and check those out, and happy study.